Hello everyone, welcome to Cryptology Academy. In this presentation, I am going to discuss the proof of the theorem which assures that the GCD of any two integers can be expressed as a linear combination of that integers. It is very interesting algorithm that will be used repeatedly in the upcoming topics of this course, especially in congruence classes and modular ring, etc. In the second part of this presentation, I am going to discuss the extended Euclidean algorithm. The extended Euclidean algorithm is a method of expressing the GCD of two integers in linear combinations of that integers. Let me first discuss the concept of linear combinations. Let a and b be two integers, and integer d is said to be a linear combination of a and b if there exist integers x and y such that one can write b equal to ax plus by. For example, for a is equal to 4 and b is equal to 7, the integers 0, 4, 7, 11, 15, 1, minus 1 and minus 4 are the linear combinations of 4 and 7. As 0 is equal to 4 times 0 plus 7 times 0. 15 is equal to 4 times 2 plus 7 times 1, and minus 4 is equal to 4 times minus 1 plus 7 times 0. So minus 4 is also a linear combination of 4 and 7. Similarly, the values of x and y for other listed linear combinations of 4 and 7 are given. Now, for a is equal to 8 and b is equal to 12, we have listed some of their linear combinations that are 0, 8, 12, 4, minus 8, minus 12 and minus 20. From the equation of linear combination of a and b, it can be seen that for fixed integers a and b, one can replace x and y with infinite numbers of integers. So the set consisting of linear combinations of a and b is infinite set. The next theorem we are going to prove guarantees that the smallest positive integer in the set of linear combinations is the GCD of a and b. For instance, in the list of linear combinations of 4 and 7, 1 is the smallest positive integer, so according to that theorem, the GCD of 4 and 7 is 1. Similarly, in the list of linear combinations of 8 and 12, 4 is the smallest positive integer, so 4 is the GCD of 8 and 12. You can verify this. Now let's prove the theorem. The theorem states that for non-zero integers a and b, the GCD of a and b is the smallest positive integer that can be expressed as a linear combination of a and b. That is, the GCD of a and b is equal to ax plus by for some integers x and y, and it is the smallest positive integer in the list of linear combinations of a and b. To prove the theorem, assume that a and b are two integers. Let S be the set of linear combinations of a and b. That is, the set S consists of those integers that is equal to ax plus by for some integer x and y. The set S must contain positive integers, 0 and negative integers. For instance, I denote the set of linear combinations of 4 and 7 by S1. The set S1 contains positive integers, 0 and negative integers. Assume that m is the smallest positive integer in the set S, which is equal to SA plus TB for some integers S and T. Our task is to prove that m is the GCD of a and b. Since a and m are both belong to S, as we have assumed that m is the smallest element of S, and one can write a is equal to a times 1 plus 0 times b, so a is also a linear combination of a and b, thus both a and b are the element of S. By using the division algorithm, one can write a equal to m times q plus r, where 0 less or equal to r and r is less than m. Here the question might be in your mind that why one cannot write m equal to aq plus r instead of a is equal to mq plus r. To answer this question, remind the division algorithm theorem. The division algorithm theorem states that if a greater than 0 and b either less or equal to 0 or b greater than a, then there exists integer q and r such that b equal to a q plus r. In this case, m is greater than 0 because we assume that m is the smallest positive integer in the set S. And a could be positive integer or negative integer, but not zero integer, as given in the statement of the theorem. So here we will discuss both the cases. If a less than 0 implies that a is negative integer, then the condition is fulfilled and one can write a is equal to mq plus r. If a greater than 0 implies a is positive integer that belong to the set S. Since m is the smallest positive integer in the set S, therefore a must be greater or equal to m, and again the condition is fulfilled. And we write a is equal to mq plus r instead of m is equal to aq plus r. I hope this is enough explanation. Let's proceed with the proof of the theorem. As we write a is equal to mq plus r, so one can write r is equal to a minus mq. Since m belong to S implies there exists integer s and t such that m equal to a times s plus b times t. Put the value of m in the equation star. The equation star become r equal to q times as plus tb. Use the distributive law of addition over multiplication. One can write r equal to a minus q times as plus q times bt. So r equal to a times 1 minus qs plus b times qt by using again distributive law of addition over multiplication. Since 1 minus qs is an integer and qt is also an integer, and r equal to a times 1 minus qs plus b times qt, therefore r is a linear combination of a and b, thus r belong to S. But r is greater than 0 and less or equal to m implies r is a positive integer in the set S that is less or equal to m. This point contradicts our assumption that is m is the smallest positive integer in the set S. So r should be equal to 0, which implies that a equal to m times q implies m divides a. By repeating the same procedure for a and b, one can prove that m divides b. Repeating the same procedure for b, one can prove that m divides b, implies m is the common divisor of a and b. To prove that m is the greatest common divisor of a and b, assume that u is the common divisor of a and b, implies u divides a and u divides b, implies u divides sa plus tb by applying fourth divisibility result that we have discussed in the second presentation. Since sa plus tb is equal to m, implies u divides m. So the GCD of a and b is equal to m. That is the smallest positive integer that can be expressed as a linear combination of a and b, thus the theorem is proved. Here we use the result that is d is the GCD of a and b if and only if for any positive integer t, if t divides a and t divides b, then t divides d. Let me construct some examples. In the example 1, the GCD of 4 and 7 is 1, and we can write 1 equal to 4 times 2 plus 7 times minus 1. In the example 2, the GCD of 8 and 12 is 4, and we can write 4 equal to 8 times minus 1 plus 12 times 1. In the example 3, the GCD of 13 and 5 is 1, and we can write 1 equal to 13 times 2 plus 5 times minus 5. In the example 4, the GCD of 15 and 9 is 3, and we can write 3 equal to 15 times minus 1 plus 9 times 2. For small integers, it is quite easy to compute the GCD and express its linear combination. However, it is quite difficult to compute the GCD of large integers and express its linear combination. For that, I am going to discuss the extended Euclidean algorithm, which is used to compute the GCD of any two integers and then express the GCD of that integers in terms of its linear combination efficiently. It is the extension of Euclidean algorithm. The Euclidean algorithm used to compute the GCD and the extension for express the GCD in terms of its linear combination. For simplicity, I will discuss the extended Euclidean algorithm with the help of example. Let A is equal to 287 and B is equal to 91. Put R0 is equal to maximum of A and B, and R1 is equal to minimum of A and B. Now compute the GCD of A and B using the Euclidean algorithm. Here the maximum of 287 and 91 is 287. So R0 is equal to 287 and the minimum of 287 and 91 is 91. So R1 is equal to 91. Now compute R2 using the general formula. The general formula is Ri is equal to Ri minus 2 minus floor of Ri minus 2 over Ri minus 1 into Ri minus 1. So for I is equal to 2, R2 equal to R0 minus floor of R0 over R1 into R1. Here R0 is equal to 287 and R1 is equal to 91. So R2 is equal to 287 minus floor of 287 over 91 into 91. 287 over 91 is equal to 3.15. So R2 is equal to 287 minus 3.15 into 91. The floor of 3.15 is equal to 3. So R2 is equal to 287 minus 3 times 91. So R2 is equal to 14. We can write 14 is equal to 287 minus 3 times 91. Since R2 is not equal to 0, so we have to compute R3. To compute R3, we will use the general formula by putting I is equal to 3, R3 equal to R1 minus floor of R1 over R2 into R1. Here R1 is equal to 91 and R2 is equal to 14. So R3 is equal to 91 minus floor of 91 over 14 into 14. 91 over 14 is equal to 6.5. Therefore R3 is equal to 91 minus 6.5 into 14. The floor of 6.5 is equal to 6. So R3 is equal to 91 minus 6 times 14. So R3 is equal to 7. We can write 7 equal to 91 minus 6 times 14. Since R3 is not equal to 0, so we have to compute R4. To compute R4, use the general formula. For I is equal to 4, R4 is equal to R2 minus floor of R2 over R3 into R3. Here R2 is equal to 14 and R3 is equal to 7. So R4 is equal to 14 minus floor of 14 over 7 into 7. 14 over 7 is equal to 2. So R4 is equal to 14 minus 2 times 7. So R4 is equal to 14 minus 14. Therefore R4 is equal to 0. Since R4 is equal to 0, therefore the GCD of 287 and 91 is equal to 7. We have computed the GCD of 287 and 91. Now in the extension part we will compute x and y such that 7 is equal to 287 times x plus 91 times y. To compute x and y, since we know that 7 is equal to 91 minus 6 times 14 and 14 is equal to 287 minus 3 times 91. Put the value of 14 in the equation star, we get the equation that is 7 is equal to 91 minus 6 times 287 minus 3 times 91. Implies 7 is equal to 91 minus 6 times 287 and minus 6 times minus 3 is equal to 18. So we write 7 equal to 91 times minus 6 times 287 plus 18 times 91. Implies 7 equal to 1 plus 18 times 91 minus 6 times 287. Implies 7 is equal to minus 6 times 287 plus 19 times 91. Implies 7 is equal to 287 times minus 6 plus 19 times 91, which is a linear expression of 287 and 91. So x is equal to minus 6 and y is equal to 19. In this example, the GCD of the given integer is R3 and R3 is a linear expression of R2 and R1. Here R1 is given and R2 is a linear expression of R1 and R0. So we substitute R2 by its linear expression, consequently get the GCD in terms of linear combination of R1 and R0, which was our main task to do. Let me do another example of extended Euclidean algorithm. Let A is equal to 81 and B is equal to 57. Put R0 is equal to maximum of 81 and 57 and R1 is equal to minimum of 81 and 57. Now compute the GCD using the Euclidean algorithm. To compute the GCD, first compute R2 using the general formula. The general formula is Ri is equal to Ri minus 2 minus floor of Ri minus 2 over Ri minus 1 into Ri minus 1. So for I is equal to 2, R2 is equal to R0 minus R0 over R1 into R1. Here R0 is equal to 81 and R1 is equal to 57. So R2 is equal to 81 minus 1 time 57. Here the floor of 81 over 57 is equal to 1. So we write R2 is equal to 81 minus 1 time 57. So R2 is equal to 24. And one can write 24 is equal to 81 minus 1 time 57. Since R2 is not equal to 0, so we have to compute R3 using the general formula. For I is equal to R3, R3 is equal to R1 minus R1 over R2 into R2. Here R1 is equal to 57 and R2 is equal to 24. So R3 is equal to 57 minus 2 times 24. Because the floor of 57 over 24 is 2, so we write R3 is equal to 57 minus 2 times 24. So R3 is equal to 9. One can write 9 is equal to 57 minus 2 times 24. Since R3 is not equal to 0, so we have to compute R4 using the general formula. To compute R4, put I is equal to 4 in the general formula. So R4 is equal to R2 minus R2 over R3 into R3. So R4 is equal to 24 times minus 2 times into 9, because the floor of 24 over 9 is equal to 2. So R4 is equal to 6. One can write 6 is equal to 24 minus 2 times 9. Since R4 is not equal to 0, so we have to compute R4 using the general formula. So by putting I is equal to 5 in the general formula, R5 is equal to R3 minus R5 is equal to R3 minus floor of R3 over R4 into R4. So R5 is equal to 9 times minus 1 times 6, because the floor of 9 over 6 is 1. So R5 is equal to 3. We can write 3 is equal to 9 minus 1 times 6. Since R5 is not equal to 0, so we have to compute R6. To compute R6, put I is equal to 6 in the general formula. So R6 is equal to R4 minus floor of R4 over R5 into R5. So R6 is equal to 6 times minus 2 times 3, because 6 the floor of 6 over 3 is equal to 2. So R6 is equal to 0. Since R6 is equal to 0, therefore the GCD of 81 and 57 is equal to R5. So the GCD of 81 and 57 is equal to 3. Now in the extension part, we have to compute x and y such that x3 is equal to 81 times x plus 57 times y. First write the equation of R5, which is the GCD of 81 and 51. The equation of R5 is given in 4, which is 3 is equal to 9 minus 1 times 6. The value of 6 is given in equation 3. Replace 6 by its equation. We get the equation that is 3 is equal to 9 times minus 1 times 24 minus 2 times 9. Now by applying the distributive law of addition or multiplication, we get the equation that is 3 is equal to 9 minus 1 times 24 plus 2 times 9. Since 1 times 9 plus 2 times 9 is equal to 3 times 9, so we get the equation that is 3 is equal to 3 times 9 minus 1 times 24. The value of 9 is given in the equation 2. So replace 9 by its equation. We get the equation that is 3 is equal to 3 times 57 minus 2 times 24. By applying distributive law of addition over multiplication, we get the equation that is 3 is equal to 3 times 57 minus 6 times 24 minus 1 times 24. So 3 is equal to 3 times 57 plus minus 6 minus 1 times 24. So we get the equation that is 3 is equal to 3 times 57 plus minus 7 times 24. The value of 24 is given in the equation 1. So replace 24 by equation 1. We get the equation that is 3 is equal to 3 times 57 minus 7 times 81 minus 1 times 57. So 3 is equal to 3 times 57 plus minus 7 times 81 minus 7, and minus 7 times minus 1 is equal to plus 7. Therefore 3 is equal to 3 times 57 plus minus 7 times 81 plus 7 times 57. 7 times 57 plus 3 times 57 is equal to 10 times 57. So we get the equation that is 3 is equal to 10 times 57 plus minus 7 times 81. Here we write the GCD in term of linear combination of 81 and 57. So x is equal to minus 7 and y is equal to 10, which was our main task to compute in the extension part.